Hello and welcome. In this video, we are going to learn about Newton's second law of motion. Now, for Newton's first law, we already know that a body cannot accelerate or decelerate without the application of a force. Newton's second law gives the relationship between the force that is applied on the body and the acceleration produced in it. Therefore, the statement of the Newton's second law is the net force on a body is equal to the product of mass of the body and its acceleration. That is, F net is equal to mass times acceleration. Now, what do we mean by F net? F net is the resultant of all the forces that is applied on a body. Suppose that we have a body of mass m and there are multiple forces applied on this body. So on this body we have four forces applied, that is F1, F2, F3 and F4. To obtain F net, we perform vector addition of all these forces like this. This is F1, this is F2, this is F3, F4, and this F net is the sum of all these force vectors. So this F net has to be used in the Newton's second law to obtain the value of the acceleration that is produced in this body. For better understanding, we will take an example. Suppose that we have a mass of 2 kg lying on a frictionless surface, and suppose that we apply a force of 5 newtons in the positive x direction and a force of 2 newtons in the negative x direction, and we wish to obtain the acceleration that is produced in this body. So the first step in determining the acceleration is to determine the net force that is applied on this body. Since F1 is in positive x direction and F2 is in negative x direction, the net force in the x direction is equal to F net x equal to F1 minus F2. Putting the values of F1, F2, we obtain F net x as 5 minus 2 is equal to 3 newtons. Next, we obtain the acceleration. So the acceleration can be obtained as follows. We know that F net x is equal to mass of the body times the acceleration produced in the body. And since the net force is in x direction, the acceleration produced in the x direction. From this, we obtain Ax equal to F net x by m. Putting the values of F net x and m, we get Ax equal to 3 by 2 meter per second square. This is equal to 1.5 meter per second square. So with the application of these two forces, the acceleration that is produced in this body is 1.5 meter per second square. Let's take another example. Suppose that we have a body of mass 0.5 kg and a horizontal force of 9 newtons is applied on this body. Another force of 8 newtons is applied on this body. This force is making an angle of 60 degrees from the negative x direction. Now we wish to obtain the acceleration that is produced in the body and the direction in which the body accelerates. To find acceleration, we first find the net force in the x and y direction. To do this, we obtain the component x and y components of these forces and then add them together. So the force F1 is in x direction only and the x component of F2 is in the negative x direction. Therefore, in the x direction, net force is F net x equal to F1 minus F2 cos 60. Putting the values of F1 and F2, we obtain F net x as 9 minus 8 cos 60. This is equal to 9 minus 4 newtons and this is equal to 5 newtons. Therefore, the net force in the x direction is 5 newtons. Therefore, the acceleration in the x direction will be equal to F net x divided by m. This is equal to 5 by 0.5 and this is equal to 10 meters per second square. Similarly, the net force in the y direction is F net y equal to F2 sine 60, since the y component of F2 is in the positive y direction and there is no component of F1 in the y direction. Putting the value of F2, we obtain F net y as 4 root 3 newtons. Putting the value of F2 equals to 8 newtons, we obtain F net y as 4 root 3 newtons. Therefore, the acceleration in the y direction is F net y divided by m. This is equal to 4 root 3 divided by 0.5. This is equal to 8 root 3 meter per second square. Now, to obtain the direction in which the body accelerates, we use this relationship. Theta is equal to tan inverse ay by ax. This is equal to tan inverse of 8 root 3 by 10, and if we calculate it, we will find it that theta is equal to 54.2 degrees. This body accelerates in the direction which is making an angle of 54.2 degrees from the positive x direction. We will take another example. Suppose that we have a body of mass 2.5 kgs sandwiched between two frictionless surfaces. Suppose that the force that is applied on this body is along the magnitude of this force is 10 newtons and it is making an angle of 60 degrees from the positive x direction. We now wish to calculate the acceleration that is produced in this body. As we can see that this body is sandwiched between two frictionless surfaces, therefore this body cannot accelerate in the y direction. This body can only accelerate in x direction. Therefore the y component of acceleration of this body is 0, and to obtain the x component of acceleration, we calculate the force in the x direction. Therefore net force in x direction is equal to F net x equal to F cos 60. Putting the values of F, we calculate F net x as 10 into 0.5. This is equal to 5 newtons. Then the acceleration we calculate as Ax is equal to F net x by m. Putting the values of F net x and m, we calculate Ax as 5 by 2.5 meter per second square. This is equal to 2 meter per second square. Therefore, with the application of 10 newtons of force in this direction, which is making an angle of 60 degrees from the horizontal direction, this body is accelerated by 2 meters per second square in the x direction. Now we will learn about some specific type of forces. The first force that we'll consider is the gravitational pull of the earth. Every object that is present on the earth experiences a pull by the earth towards its center. That pull is called the gravitational pull of the earth. Therefore, the pull exerted by the earth on any body is the gravitational pull of the earth. And in all practical cases, this pull is directed vertically downwards. Now suppose that we have a body of mass m and the free fall acceleration is g. That means if body is allowed to fall freely, it will accelerate by g amount. Also from Newton's second law, we know that F is equal to ma. Since g is in the negative y direction, therefore a is equal to minus g, and also the gravitational pull is directed downwards, and if we denote gravitational force by Fg, this Fg will be equal to minus of F. Therefore, we can write minus of Fg is equal to m times minus of g, and from this we obtain that the gravitational pull of the earth is equal to mass times the free fall acceleration. We can also write this in the vector notation as follows. In vector notation, we can write vector Fg, this is equal to minus of Fg times j hat, where j hat is the unit vector in the positive y direction. Putting the value of Fg, we write vector Fg as minus of m times g times j hat. Now minus of g times j hat is the vector g, therefore vector Fg is equal to m times vector g. So in the vector notation, we can write gravitational pull as vector Fg equal to m times vector g. The next force to consider is the weight of the body. The weight of a body is the net force required to prevent the body from falling freely as measured by someone on the ground. That means, as per an observer on the ground, if the body is constrained to fall, if the body is not falling, the force that is required to keep the body in this condition is called the weight of the body. Now suppose that we have a body of mass m, and we already know that the gravitational pull of the earth is Fg. To keep this body from falling freely, we have to apply a force in the upward direction. We call this force as the weight of the body denoted by W. Now from Newton's second law, we can write W minus Fg. This is the net force on this body. This is equal to mass times acceleration, which is 0 in this case as the body is constrained to fall. From this we can write W as equal to Fg. That means the weight of a body is equal in magnitude to the gravitational pull exerted by Earth on the body. Now, the next force that we will consider is the normal force. Body is pressed against a surface. When a body is pressed against a surface, that surface deforms and it pushes on the body with a force that is perpendicular to the surface. This force is called the normal force. So, a normal force is a force experienced by a body when it is pressed against a surface, and the direction of the normal force is perpendicular to the surface against which the body is pressed. Now suppose that we have a body of mass m and it is lying on a surface. This surface may be accelerating or it may not be accelerating. Suppose that it is accelerating in the y direction by ay. Suppose that this surface is accelerating by ay. This situation occurs when this object is inside a lift which is accelerating in the upward or downward direction. So along with this surface, this body is also experiencing the same acceleration ay, and also this body is experiencing a gravitational pull of the earth which is equal to Fg, and the normal force on this body is Fn. So the net force on this body is Fn minus Fg, and this is equal to mass times the acceleration which this body is experiencing. Now Fg is equal to mg, therefore Fn minus mg is equal to m times ay. Rearranging it, we obtain Fn equals 2m times g plus ay. This means that the normal force experienced by a body of mass m which is lying on a surface, that surface is accelerating by ay. The normal force in this case is mass times sum of free fall acceleration and the acceleration that the body experiences by direction. Next force that we'll consider is the frictional force. A force which opposes the sliding of one body over another body is called the frictional force. Suppose that we have a body and it is lying on a surface that is frictional. And if we want to slide, if we attempt to slide this body on this surface, this body will experience a force in the opposite direction which resists the movement of this body. This force is called the frictional force. This force is called the frictional force. Last force to consider is the tension. Suppose that we have a body and a rope or a cord or any other such object is attached to the body, and this cord is pulled. The cord then pulls this body with a force equal to T and which is directed away from the body. This force T is called the tension. This cord is usually massless because the mass of this cord is very small compared to the object being pulled. and it acts as a connection between two bodies. Therefore, this cord is acting as a connection between this body and this hand, and it is pulling both the bodies with the same force of magnitude T. This cord is pulling both the bodies with the same force of magnitude T. The force is always same even if the cord runs. The force is always same even if the cord runs around a massless, frictionless pulley. For example, here and here. That's all for today. In the next video, we will discuss Newton's third law of motion along with some examples on application of Newton's laws of motion.